Welcome to today's oral history as part of the MEMS Technical Community. We're reaching out to leaders in our field to hear their stories and understand what led them down their career paths. And I'll be your host for today's session. With us today is Dr. Nico de Rooij, who is Professor Emeritus of EPFL and the former Vice President of CSEM SA. CSEM, as it's known, is a Swiss research and development center focused on precision manufacturing, digitization, and renewable energy that follows a nonprofit public-private partnership model. Dr. de Rooij received his BS and MS degrees in chemistry from the University of Utrecht in 1972 and 1975 respectively, and his PhD degree in chemistry from the University of Twente in 1978. Prior to his appointments at EPFL and CSEM, he worked at Cordis Europa in the Netherlands and the University of Neuchâtel. He is recognized as a leading international researcher in the design, microfabrication, and application of miniaturized silicon-based sensors, actuators, and microsystems. Dr. de Rooij, thank you for taking the time from your busy schedule to be with us today. Let's start our conversation with your early years. Can you tell us when and where you were born and share some early memories of your family life?
I was born in 1951 in a city in the southern part of the Netherlands, close to the Belgian border. The city has the name Bergen op Zoom. All these cities in that part of the world, they date back to the Middle Ages, so they have very old city centers with historical buildings and huge churches and even maybe small palaces of the important people in the late Middle Ages when this part of the world was very flourishing. So I grew up in that city and did my schools, and already during, I think, my probably high school time, I got interest in electronics, but also in physics and chemistry. And I think when I was a young boy, we got these kind of new toys like Lego. So probably I was already quite enthusiastic as a boy to play and to build all kinds of devices and systems with Lego bricks. And the very first Lego bricks probably must be in the mid, somewhere in the early 60s. And we got also Meccano, and then you could somewhat introduce also electric-driven motors in these systems. So I was quite interested in playing and building, let's say, small cars, vehicles, using all these toys.
What was it like growing up in Bergen op Zoom?
Bergen op Zoom was a really very pleasant city, close to an environment where we have a forest and also close to the North Sea. So I remember as a child, first of all, for the summer holidays, we went mostly to the coast, to the North Sea coast. So that was always very, very nice. And later, being probably a teenager, then with friends, we did biking, go to the sea, having our tent on the bicycle, and then stayed a few weeks for the summer holidays and having a good time.
Sounds like a lot of fun. Can you tell us about your parents, and did you have any siblings?
Yeah, my parents dated also from that region. My father was an accountant in a transport company, and my mother had training as a medical nurse. So yeah, I have one sister, so we had always a very pleasant family life with quite a lot of cousins and also family nearby. So I remember very well the family parties we had to celebrate anniversaries of our grandparents and of course also of our aunts, and it was a very good time.
Great. Please tell us about your early school years from primary and up through high school. What kind of student were you, and maybe what were your favorite subjects?
I would say that I was certainly a student who was probably quite calm, not a revolutionary guy, but just doing my work, my homework, probably good enough to get to the next levels. I would say not nothing really particular. It was primary school was probably quite easygoing. The high school was more challenging. We got in these days in the Netherlands, the school system was still quite demanding. So on the one hand, you had to do, of course, the mathematics, the physics, the chemistry, but also you got quite a language program. So you had to do 3 foreign languages. That was compulsory. So German, French, English. Then, of course, the Dutch language, because that was your mother tongue. And the track I was following was called Lyceum. Yeah. On top of that, we had also to learn quite a bit on Old Greek and Old Latin. So that means a lot of work which was based on memorization of your of words and translations. So it needed quite some effort to make it, but this went also quite fluently, quite easily at the end, and I passed my exams. And at the age of 18, then I was allowed to go to a university.
Yeah, but in high school, what was your favorite subjects?
Well, I had definitely a preference for physics and chemistry, because also I think we had at that time perfect teachers who did a lot of experiments. It was just not looking in the equations or making the exercises, but also bringing in equipment, doing experiments where we could also be involved. So that I really found very interesting.
Great. When you were younger, what would you and your friends do for fun?
Oh, we probably did a lot of things which were bad or not allowed to do. But also I think with some friends we got interested in these days making maybe equipment for music amplifiers that you could probably get some music louder and so on. So that was certainly a time where you had in these days you had you see not yet a CD player or the video. You had still the old disc.
The records?
Records, yeah. And sound quality was maybe not always very good, so people tried to build their own loudspeakers. And I think we had quite some a group of friends where we tried to have fun with listening to the music and maybe also getting equipment improved.
So did you have any other hobbies as a child?
Well, I was not really a strong man in sports, but I tried to do a few things like swimming and hiking. And yeah, for the rest, I would say certainly a calmer life. I know that worldwide in the 60s, so let's say the period 60, 61, 62 to the early 70s in Europe, I don't know how to, also in the United States, I guess, at universities, but also at schools, it was quite a period of revolutions. 68? Paris was a big thing. Students went all crazy. In the Netherlands, we had also that at universities, students occupied the central administration buildings and tried to change the laws. I was probably observing this all, but not really involved in getting fights with the police. But these were quite hectic days, so to say. The second half of the 60s. Yeah, and that certainly impressed me in a way. I have to admit that I was certainly not the guy who was at the front of challenging police and throwing with all kinds of objects.
I see. Were there any early events or mentors that influenced your trajectory towards science and technology?
Well, I think I had probably the chance to have, as I said before, at the high school, the teachers for, in particular, physics and chemistry, who did a lot of hands-on experiments, and that certainly encouraged me and stimulated me to follow that more, let's say, a track on later on studying these disciplines.
I see. Can you tell us anything about your time in college and how you decided to go to the University of Utrecht?
The reason was, well, there are maybe several reasons. First of all, well, you left your your hometown. You go, let's say, far away. So that means for Dutch, how to say, dimensions, or everything is of course relative, but you're going to live as a student in a student house, and then once a month you go home. So you probably still look for a place which is not too far away. I think this Utrecht from the city where I was born was maybe a train ride of 2 hours or something like that, what I remember. It was also a good place. It had a very dynamic environment. Many students, 20,000 or 30,000 students already in the late 60s. A lot of choices you could make there for, let's say, the disciplines you like to follow, and also a very, very dynamic student life. An old city as well, with a historical center, a lot of cultural activities. So I liked it there, so I decided to enter that university.
I see. Now, you said your high school teachers had a strong influence on you in both chemistry and physics. Ultimately, you decided to focus your undergraduate degree work in a chemistry focus. Why did you make that decision?
Well, I'm also there. Probably the professors at the university, they had quite a lot of interesting programs, and these days surface science became very how I would say a new field, basically, where just the tools became available to study really what happens on surfaces of, let's say, single crystals by doing optical techniques, but also so-called what was it called again? Low energy electron diffraction. You could really see how, let's say, certain gas atoms could absorb on the surface of a single crystal, and you could already get information on, let's say, atomical or nanometer dimensions, how certain atoms could absorb on surfaces. So we had these days the tools there, and this was a very intriguing field. So probably also one of the professors who started that surface science activity at the University of Utrecht inspired me, and I decided to let's say, to do my master project in the area of surface science.
Before you went to your master's, did you get involved in any research as an undergraduate
Well,
student?
as undergraduate, you probably follow more the disciplines you have to do to get the basic knowledge. So that means the whole program of mathematics, basics in physics and chemistry. And there was maybe less real research. It was more getting the skills and the basic knowledge, which then you apply later more in your master's style.
Right, but then when you finished your bachelor's degree, you decided to go pursue a master's and not, I suppose, like many of your colleagues at the time who may have gone off to get a job in industry. Why did you decide to get a master's?
I think at that time was still considered, if you finish with a master, you have definitely better prospects and better opportunities to qualify for jobs, either in industry or academic career. So there was, I think, not that much of debate to stop already after a bachelor degree and go for a job. I think most at these days, I'm talking about the early 70s, most of my student colleagues, we went on to finish at least with a master.
I see. What was the focus of your master's thesis?
That was basically a study on related to surface science, and basically studying as far as I remember, the absorption of oxygen molecules on a surface of single crystal silver. Don't ask me now why, but probably it had to do with maybe catalysis, or people try to understand the very first reactions, what happens at the surface when atoms adsorb and how they get arranged and how they finally react with the solid state surface. And in these days, as I mentioned, tools became available that you could see this on with great resolution already. It was before the atomic force microscope became available, but as I mentioned, optical techniques like ellipsometry, but also that low energy electron diffraction, and another technique was called Auger spectroscopy, where you could also detect and discriminate between the various elements. So they all became available in ultra high vacuum systems. Quite a lot of heavy stuff, and yeah, so I thought it was very nice and very interesting.
I see. Now you mentioned that many of your colleagues went on to get a master's. But you decided to go on further and get a PhD, and perhaps many of your colleagues stopped with a master's. Why did you make that decision?
Well, I was still probably motivated to continue with to finish with a PhD, because at that time it was probably good to have to not finish with a master, but to continue to further perfection your level of knowledge. And there was also an opportunity, since I was working in, let's say, a laboratory focusing on surface science. We were, of the professor of that lab, his name was Professor Bootsma, who passed away at a relatively young age. We were contacted by a research team from the University of Twente, which is an engineering school. And this is maybe then the start to the next phase. They had developed, and his name was Professor Piet Bergveld. They had invented and were trying to understand the operation of a chemically sensitive field effect transistor, or also called ISFET, ion sensitive field effect transistor. So a real microelectronic devices, but they were able to make it sensitive to chemical species, but the mechanism was not very much understood. And this had all to do with what happens at surfaces. So being involved at a laboratory of surface science, I got the contact then to this engineering school, and that was a real opportunity. We're talking about still the early 70s, so field effect transistors, so CMOS was not really established. I think MOSFETs, P-channel MOSFETs were probably already used. They were stable. CMOS was still in the early days. This was really the time where a lot of pioneering work went on, also in the Netherlands, still on the solid state work. And this mixture and this, bringing together several disciplines, microelectronics, material science, interface science, was very attractive for me, and I took up that challenge.
I see. So your first engagement with the field of micro-scale technologies and microfabrication was during your doctoral work?
Yeah, well, having that contact, and then I was basically offered a PhD position at the University of Twente, engineering school, with the mission to clarify or to try to understand the mechanism, how such a field effect transistor could be chemical sensitive. And of course, many people were saying, well, you are crazy. We, the people there, the real microelectronics engineers and circuit designers, they said, well, we try to do our best to package these devices the best we can, never expose it to humidity or to aqueous solutions or whatever. And you guys try to keep the gate area open and expose it to liquids. That's very bad. But it was a start of basically the early days of what later became then MEMS or transducers. So having these simple transistor devices already fully microfabricated, expose it to aqueous solutions and see that it reacts on changes in pH or other changes in ion concentration. So, and I think we successfully then were able to find and understand the mechanisms, how these transistors worked, and there were then also really efforts to get it transferred to industry in a later phase.
I see. Now, speaking of industry, after you finished your PhD, you decided to go to industry instead of becoming a professor. What prompted that choice?
Well, the fact that we had these early devices more or less understood, and also already a trend there to cooperate with industry, if let's say universities could bring solutions to maybe to certain questions in the industrial environment. And we had I think in the Netherlands I'm talking here about the mid-70s, good opportunities. It was a time where quite some leading US companies settled down in the Netherlands with R&D units and also manufacturing units, especially for medical devices. And I would like to cite one particular company called Cordis, founded in Miami, Florida. And the founder was Dr. Bill Murphy. And I had the chance to meet Dr. Murphy at several occasions. So I think they were very successful with the pacemaker business, but in addition, they had also a production line of so-called angiographic catheters to introduce in the arteries and to inject certain liquids, and then with these angiographic catheters, you could make X-ray observations and really see the functioning of the heart valves. That was the main function of these catheters. And having these small sensors, the idea was basically if you can equip these catheters with very small sensors and then measuring, for instance, blood gases in critical care conditions, that would be a major step forward in following the status of patients when they are in IC units, intensive care units. So that was basically a fantastic challenge, and there was a strong hope that this new technology could be combined with all the technology and know-how, for instance, in these medical electronics companies. So Cordis was very motivated to explore new technologies, to combine that with their, let's say, standard products, and then bring new innovations.
I see. Were you able to bring some of your PhD experience and research outcomes to their...
Absolutely. So that was probably in a period where maybe tech transfer was not so understood or not so daily practice, but I think we probably had the chance to do it. So being skilled for my PhD work and also doing the micro manufacturing, that means making the devices, go in the clean room, learn about all the steps like the photolithography, the etching, ion implantation, of course with simple tools. And then having that contact with Cordis in the Netherlands, in the R&D division, I had really a great opportunity that we also transferred quite a bit of this knowledge of how to make simple devices in a clean room. That Cordis decided to build their own clean room, and I was basically given the task to set up that rather simple clean room, but allowing the company to fabricate in their own premises. Let's say these chemical sensors first, and later on added also pressure sensors of small size, and then of course there were project teams having these sensors available. They built it then in the catheters, and then a very fascinating period started of animal experimentation. And then also clinical studies started. It took, of course, several years, but it was a very fascinating period.
I see. So your work at Cordis was from 78 to 82, and you're working on miniaturized sensors integrating into these medical products. Can you talk about your first MEMS conference and the early impressions you had about the field and papers presented there?
Yeah, this was a great coincidence, basically. I'm talking here about the late 70s, the early 80s, and already at the university, at Twente University, but also even before. Later on at Cordis, there was always a willingness to publish, probably make sure that you had done the right IP protections, but there was a strong a strong motivation to get things published and also to go to conferences. So probably I was in the privileged position together with many colleagues to be able to go to conferences and to present. And I remember very well that the what's called the precursor, or sometimes even called the first transducer conference, was a large MRS meeting, Material Research Society meeting, in 1981 in Boston. And it had probably 8 or 10 or 12 symposia, all focusing on particular fields. And there was one particular symposium which had as title Solid State Sensors and Actuators. And there, for the very first time, I had the chance to meet so many future colleagues already from MIT, from Stanford, and other places. And during that conference, which was organized by late Professor Wen H. Ko and Dr. Scott Chang, to my best knowledge, from General Motors, with other colleagues, it was decided, in view of the very strong interest, not to continue with another symposium within, let's say, Material Research Society, but really decided to make an independent conference. And that decision was then followed up by the very first Transducers conference in 1983 under the leadership of also late Professor Simon Middlehook. And yeah, that was then really the start of where we are today, basically. Many Transducers conferences followed. And yeah, I was probably a very privileged person to be involved and to have assisted at the very first editions and meeting there, the leaders of that field, in particular from the United States, so Steve Centuria, but also Richard Muller and many more to cite.
Yes. Now, after those 4 years at Cordis, you decided to take a job as a professor at the University of Neuchâtel.
Yes.
Please tell us about that career change.
Well, what basically happened due to our activity in not only making devices and studying them and getting them into product, but also publishing, apparently then in a certain community, your name might be, you probably get a certain, the people might know about you. And what happened in Switzerland, which in the western part of Switzerland, where Neuchâtel is located, there was, of course, a very flourishing watch industry, which had always golden years, but then somewhere in the mid-70s, suddenly the mechanical watch industry was challenged by the arrival of quartz watches, which were much more precise, which Switzerland had not decided to mass manufacture these devices, although first prototypes were developed and demonstrated. And then suddenly Japanese watchmakers, in particular Seiko, followed by watchmakers of the United States, I might have the name wrong, but I remember Timex, they took over basically the market. So in Switzerland, this was like an earthquake, a very dramatic impact on labor. And the, let's say, the western part of Switzerland, let's say the area between Geneva up to Basel, what they sometimes call the Jura, there was a heavy loss in jobs, and it impacted really the whole community there. So decision makers, politicians, but also decision makers at teaching centers, they came to the conclusion that they should look to new technologies, probably also educate the future engineers and scientists in new areas, which maybe could replace the traditional watchmaking. And they saw the field of sensors as an important field. Switzerland had already a flourishing sensor industry, maybe more conventional. For instance, if you talk about chemical sensors, I think probably all the suppliers of so-called pH glass electrodes where you blow it by a glass blower. Well, in practice it might be done differently. They mostly all come from Switzerland. So it had a long tradition in high level, very, very reliable sensors. And they saw the opportunity in that area, which was heavily impacted by job losses, to go in new fields, new directions. And in Neuchâtel, a small university, they had an institute called Institute of Microtechnology. They decided to create a new chair focusing on the field of microsensors, microactuators. And since I was active in that field, I was invited to apply for the position. And probably, most probably, again, a strong privileged situation in my life. At the end of the recruiting campaign, I was offered the position. And I saw this as such a fantastic next step in my career, so I didn't hesitate 1 second and said, yeah, let's go there. So I moved with my family, my wife. She was pregnant 7 months already. We had already 1 child, and then we still said, okay, let's order a truck, and here we go.
So that wasn't part of the University of Neuchâtel?
Yes. And also over the years, the structure changed, but for many years I was then working at the institute, which was part of the Faculty of Science of the University of Neuchâtel. It's a rather small university, cantonal university. And then later this Institute of Microtechnology, we have been integrated in the EPFL, so the Swiss Federal Institute of Technology, the EPFL, that means École Polytechnique Fédérale de Lausanne, that's in the French-speaking part of Switzerland. You have the well-known ETH Zurich, #1 university, at least in Europe, and maybe always in the top 10 ranking. And in the western part of Switzerland, the second school was established many years ago, EPFL. And then in the 2009 or so, after many years of negotiations, the IMT, Institute of Microtechnology of University of Neuchâtel, was integrated into the EPFL.
I see. And then you continued on as a professor there leading that. But then later you also became vice president of CSEM.
Yeah, things are always, probably as every place in the world, there are always many, many things happening. So as I told earlier, the Swiss watch industry maybe didn't recognize the importance of the quartz watches when the point to make a major decision had to be taken. But they had already established a research center to develop these quartz watches, and they were able to make and demonstrate prototypes. And that center who did all this work was called CEH. It's French for Centre Électronique Horloger, like electronic watch center. And that was also located in Neuchâtel. And that center also has grown over the years and became in 1984, after a merger with some other corporate research units belonging to the watch industry, that became CSEM or XEM, so Swiss Research Center for Electronics and Microtechnology. And since at the university, or later on EPFL and CSEM, we had, of course, very close ties. Neuchâtel is a small city, 30,000 people. We had very close ties and even shared facilities and shared clean rooms. So at a certain point in time, it was considered as the best way to cooperate and also to be efficient as in all ways, that a shared position would be extremely good to assure, on the one hand, that with the mission of a university, you take care in the right way about your students, undergraduate, graduate, PhDs and postdocs. And on the other hand, for the more applied, more industrial type of projects you could also do, the CSEM would be the better environment. So in my case then, the decision was taken that I would have a 50% job being a university professor at EPFL, and the other 50% running a research team within the XEM.
I see. So looking back, who played a significant mentorship role in your career?
Yeah, if you go back to the early days of, let's say, solid-state sensors, actuators, and microsystems, later, or as we call it now, transducers, definitely I had the chance to meet, let's say, the fathers of this field in Europe and in the United States. So, of course, I should mention, first of all, my mentor and PhD advisor was Professor Piet Bergveld, the inventor of the ISVET, who got, I think, a worldwide recognition for his invention. And then also in the Netherlands, at Delft University, there was Simon Middelhoek, who really was the very, very well-known person, also with a strong worldwide recognition. And I think he is sometimes called the father of the silicon sensors. He was promoting this and doing a lot of effort. And I had the privilege to be in contact with him, and he has given me very important advices, and he also has been very supportive for my career path. And then, of course, in the United States, I had very good contacts and strong relationships with Jay Zemmel at Penn University. He came already during my PhD thesis work. He visited many times Piet Bergveld, and also we had sometimes the opportunity to visit his lab in Philadelphia. And another person I definitely should like to mention, other two persons, definitely Steve Centuria from MIT and Richard Miller from Berkeley. So I had the privilege, as I said, to have also strong contacts to all these pioneers of the field what became MEMS. I think it was even Richard Miller who coined the term MEMS, as far as I remember. And they have been always very supportive also and have given me always very good advice for my career path. So I'm very grateful. Certainly I forgot a number of important persons, but the 3 or 4 persons I mentioned, I have also during the many conferences which followed, have always a very good contact and relationship.
Right. When you think about your research career, are there particular projects that you are most proud of, or that you think were particularly interesting?
Yeah, what probably very many labs did in the early 80s, making maybe the rather standard devices like pressure sensors and accelerometers or chemical sensors, are all in a very early form. And that we also did and try to understand and try to improve either on design or the technology, but really integrate these devices into more complex systems was maybe not so much done. And I think due to context and also due to proposals which came from in particular in Europe, from the European Space Agency, at a certain point in time, we had an opportunity to submit a proposal to build a bioreactor of small size, which was planned to be used on space shuttle flights, with the idea, with the objective to investigate the influence of microgravity on the growth of yeast cells. And yeast cells are probably a model system, very well known by biologists, and having these yeast cells exposed to, let's say, 10 days or 16 days flight on the space shuttle circulating around Earth, that could then give new knowledge about basically the influence of microgravity on the growth conditions of these yeast cells, and that could probably have strong impact on if human beings would stay a long time in microgravity. So to make this proposal successful, we proposed to use basically for this bioreactor a number of MEMS-based components to control what happens in the bioreactor. So we needed the chemical sensors. Therefore we could use and propose to use pH, ion-sensitive field effect transistors. But also in such a bioreactor, you have to renew the nutrition, the sugar solution, which is needed to keep alive your yeast cells. Therefore, there we came up with the idea to use a silicon microfabricated pump. And again, to get this pump operating in a reliable way, we had to complete it with flow sensors to operate it in a closed loop condition. Make sure that it all works reliable and you can dose the right volume of the nutrition. So there, at the end, we were really able for the first time, at least for our lab, to make a system having sensors, microfabricated or MEMS type sensors and MEMS type actuators all in a system. And the good news was, and it was extremely stimulating also for the PhDs and the postdocs who were involved in this project, that this bioreactor was then used on 3 space shuttle experiments. So, and this has given the opportunity for 1 or 2 postdocs and I think 1 or 2 PhD students to stay a while also at Cape Canaveral and to assist at the launch and to have the interaction during the space shuttle flight with the astronaut, because then during the space shuttle flight, the astronauts had to do certain experiments. They had to take out of the bioreactor samples and do certain manipulations with these samples, and that needed basically a communication between Earth control and people in the space shuttle. And what I learned, I was not involved personally, or I was not assisting personally, but my postdocs and PhD students, they were extremely excited, and this was such an encouragement for these young researchers to not only to, let's say, make devices and test them in the lab, but see it also applied in a very fascinating environment, very challenging environment, and also seeing that if you bring sensors, actuators, and the control electronics all together, you get really systems which quite unique performance. So I would say that was definitely a very strong, a very important highlight of the research efforts in my laboratory, and I thought it was very stimulating also for the students.
Thank you. Looking forward now, are there any challenges and opportunities in the field of MEMS today that you are the most excited about for others to advance?
Well, we are probably still in a phase where there is much more to come. So I think the technology and the manufacturing tools might be well in place to produce millions and tens of millions, and even there are visionary people who talk about the trillion sensor era. But we are also all aware that having so many devices, and they might consume still power consumption. And to make it really happen that you can use them in these large volumes for environmental control, health control, they are challenging to reduce power consumption to probably as close as 0. And is this possible? I think probably there are still important efforts needed to reduce power consumption to a level that indeed these large volumes can be used in a way that the power consumption is definitely under control. So there I see a strong challenge still.
I see. Now, if you were a student today, which area of study or research topic do you think you would pursue? Or another way to think of this is if you were advising a new student today, are there any particular avenues for discovery or research that you might encourage them to pursue?
I still, after many years of, let's say, own experiences and maybe privileged conditions in the past, but to have hands-on experiences in a lab environment, working with material, working with having exposure to technology, working in an environment where you create a device, where you build a device yourself, where you see how what can go wrong as well. You will learn a lot of this. So I would still strongly advise that people do hands-on work, do microfabrication, nanofabrication to learn and also to see how it really goes in practice, because that's extremely stimulating, but also it will help a lot in bringing additional creativity. By doing this, you will make also discoveries. So I would strongly advise and stimulate that students still do practical work, do hands-on experiences, are not afraid to go in clean room environments to work with complex equipment, and then at the end of the day see what they created, what they built, and then go and test it and probably see where there might be improvements. So I believe that this cycle is a good cycle and will definitely stimulate and encourage and be the basis for further progress.
Thank you. Finally, today, do you have any activities you like to do outside of engineering or hobbies?
Well, as you mentioned already, introducing me with the CV, I'm now retired since 2016. So basically I'm in a retirement phase where you also see that although still following what happens in the field, your daily contact is less, and you certainly are in a way in an evolution where you probably get more and more decoupled from the daily progress. But I still try to follow, let's say, main directions, and my involvement these days is more looking also to certain historical aspects, also involved in particular in Switzerland, where what I just say, the watch industry had its crisis, but is again on track. And even mechanical watches use these days also a lot of MEMS devices, and that improved a lot of performance. So I'm personally involved in a certification organization who is certifying watches for getting the status of a certified chronometer according to an international ISO norm. So that's quite fascinating to see that with very tight tolerances, even mechanical watches using MEMS technology are able to improve their performance. So I'm following a little bit this, and also working on some historical projects. I over the years learned that, for instance, the mankind is developing since many centuries techniques and possibilities, and to know time. Maybe they started with very simple tools, looking then to the stars, and ending up these days with atomic clocks. So that's a very fascinating field where I get more and more involved in more the historical pathway. So that's very challenging. So one of my current interests is trying to get an exhibition in place in the year 2025 to celebrate an invention which was made 350 years ago by a Dutch scientist. His name is Christian Huygens. And Christian Huygens, he was very instrumental in developing the pendulum clock. And people in the 16th and 17th century, they needed clocks to know exactly their position. They could maybe see, with looking to the sun or the stars, know the latitude, but never the longitude. And therefore, they needed precise clocks. And Christian Huygens did an strong improvement in getting pendulum clock, but on sea, this is still difficult. So instead of using a pendulum, he invented and published in 1675 what they call the hairspring, the spiral. And this is still used in watches. Now we made it of silicon. We call it the MEMS-based hairspring. And we would like to set up with colleagues an exhibition in 2025 to celebrate the 350th anniversary, going from very basic metal to MEMS and still a source of inspiration and innovation today. So that's what keeps me busy currently.
That's wonderful. Well, Professor Nico de Rooij, thank you so much for taking time out of your busy schedule to be with us and sharing these stories of your career. We really appreciate it.
It was a real pleasure. Thank you.